Tonight, we thought it would be a wonderful opportunity to bring in Dr. Owen Gingerich. Owen Gingerich was taught the history of science, a professor here at Harvard. He is also an astronomer with Smithsonian, but he is an author, he is a world traveler, he is a lecturer. And whenever we have questions about how the past has influenced the future today, it's Owen. I wander down to his office, look at his magnificent books, and we just talk. So tonight, I thought what a wonderful opportunity for us to begin and close our season for this spring and talk about the upcoming transit of Venus and Dr. Owen Gingerich.
Well, thank you, everybody, for coming. It's such an enormous crowd, and I hope that those of you in the classroom are able to hear and see this as well. It happens almost every time, not when I talk, but when it's mild outside and the sky is so blue, and you just get a big crowd here. Macavity, Macavity, there's no one like Macavity. He's broken every human law. He breaks the law of gravity. His powers of levitation would make a faker stare. And when you reach the scene of the crime, Macavity's not there. When I concentrate on the transits of Venus, I often think about T.S. Eliot's Mystery Cat. The orbit of Venus is tilted to the Earth's orbit by 3 1/3 degrees, which means most of the time when Venus lies between us and the Sun, what we call an inferior conjunction, the planet is above or below the Sun in the sky. A transit, when a planet is silhouetted against the Sun's disk, can only occur when the inferior conjunction occurs within 2 days of the Earth's being on the line of intersection of the tilted planes. That's the so-called line of nodes. The Earth crosses that line twice a year, nowadays on June 7th and December 8th. But like Macavity, the Mystery Cat, generally Venus is not there. So let me show you a little bit about orbits. My eyeball is the Sun, and this is the orbit of Venus going around the Sun. And so we have to tilt this a little bit so that typically it won't block off my eyeball from you people who are the Earth. Okay, I'll move around so you have a chance to see this up above. Okay, I'm going to mark that special place on orbit where the where that tilting takes place. That's known as a node. And I'm going to put one of them on this side of the hoop. That's one of the nodes. And now we need another one exactly opposite. Let me put this one, as best I can, directly opposite to be the other node. Now, as the Earth goes around, it will go past this node point, as I said, twice a year. And one time here, that happens in June. One time over here, that happens in December. But typically, Venus is not there. But there's something odd about Venus and the way it goes around, because it's almost in resonance with the Earth's orbit. So that when the Earth has gone around 8 times, Venus will have gone around 13 times, almost exactly. And so if you have a transit, as we did in 2004, 13 times for Venus later, and 8 times for the Earth, 8 years later, it's going to be practically back in the same position, and so it will happen again. But it isn't exact, and it keeps moving around slowly And so 8 years from now, there's not going to be a transit. And 8 years after that, not either. It's going to take a long time because it moves around so slowly. So now I'm going to show you on the slides a little bit more about this interesting pattern. Someplace I have a magic thing that will make the slides move. There we are. Can we get some of the upper lights down? All right. So there you see the orbit of Venus, and here is the orbit of the Earth. And this line is what we call the line of nodes. That's the line where the orbit of Venus is tilted with respect to the Earth's. Now, if we change the frame so that it's the Earth that's at the center, we can see the paths of Venus, and you can see the way it loops around in making 5 positions where it will come very close before it then repeats again. And you will notice in the detail over here on the other side that it will be slightly different, so that it will not come out exactly the same in 8 years from now. Well, there's the line of nodes, and you can see that at one of those very close approaches, and it has to be a very close approach, the one that happened in 2004 will come back again this year, 2012, and then because the whole pattern is moving around very slowly, it's not going to happen again for quite a long time. So here, those spokes are the 5 places where Venus is coming close to the Earth in this pattern. 5 close approaches in 8 years. It's almost magical the way it works for Venus, because it doesn't work that way for any of the other planets. They have patterns that come back and repeat, but not so quickly as 8 years. Now, to have this transit, you have to have Venus close enough to the node when it goes by. But it doesn't have to be exactly at that point. So it means that a transit can happen a day earlier or a day later from that magical moment. And so you see how it was in 2004 when Venus crossed in front of the Sun. It was in this lower part of the Sun. And this year, on the 6th of June, it's going to be on the other side because the positions are like this. It's then, if we look, where will it be at 8 more years, 2020, it's going to be over here someplace, and it's just going to miss. It will go slightly above the face of the Sun instead of going like this. So I'm sure you all noticed that it's sort of odd that it happens every 8 years, I mean in pairs, 8 years at a time, and then it doesn't happen for more than a century. Eventually, as this goes around, you will get a situation where Venus gets right on the node, and then there will only be one, and not 2 of them 8 years apart. But that's many centuries in the future, so don't worry about it. Now, Mercury, fast little planet, much closer to the Sun, it's easier for it to have a transit because being closer to the Sun and having its orbit slightly tilted, it nevertheless is pretty much in the direction of the Sun. So when it goes around, there is a much better chance that Mercury will go across in front of the Sun. So I just thought I would show you some of them because you get a Mercury transit about 14 times a century. And as I was making this little chart, I noticed something very interesting. I could pair them like in these two columns. You notice that here in 2006 and 2016, it was 10 years later, November to May, and in 2052 and 2062, it's also 10 years later. And if you go down, you can see that the pattern over here, the spacing, is the same as it is over here. So can you guess when the next one in the series would be? Those of you who are really fast with your arithmetic will notice that it's exactly 46 years from one side to the other. Did I hear a number first? 85. You got it. Okay, so that's the pattern for Mercury, but it's too common. Sometimes it will happen, of course, on the other side of the world, and you don't have a chance to get it. And even if you've got dark glasses, you're not going to be able to see it with your naked eye on the sun because Mercury is too small. Venus, on the other hand, if you've got really good eyesight, don't stare at the sun on June the 6th, hoping to see it unless you've got some welder's glass or something. But then if you have acute vision, you have a chance of actually picking it up with your naked eye. Well, I was always puzzled when I was much younger and an amateur astronomer as to how much calculation did astronomers have to do to get some of these interesting statistics. You just heard David tell you about this supermoon and so on. How can you calculate when something like that is going to happen? That is, strange little statistics. But more interesting is the question of eclipses. And it's kind of interesting to ask what makes an eclipse long? Because a total eclipse of the sun is typically 3 or 4 minutes in length. And going to see a total eclipse of the sun is very dangerous because it's highly addictive. If you've gone to one and it's over, as one of the astronomers in the 19th century, he felt like such a fool, such wasted time when all of a sudden it was over. And then you have to go to the next one and so on. Well, so how long can you get an eclipse to be, and what makes it long? Well, the moon's orbit is not centered on the Earth, but it's a little off-centered so that sometimes the moon is actually closer than other times. Where it's close is, of course, makes the moon appear larger, and therefore it blocks out the sun longer, and it makes the eclipse longer. If the moon is too far away, it won't even cover the entire sun. And so you get the ring, the so-called annular eclipse, and that's what's coming up very shortly.
The ring of fire.
Yes, you set it up for me. The ring of fire. The annular eclipse, and in fact, more of the eclipses are annular than total. So it's just that they're interesting to see if one of them is happening within the 100 miles or so of you. It's worth making the drive just to go and see it. Among other things, it's so much fun to see the shadows through the leaves, where there are little sort of pinholes, and you look under the tree, and instead of normal shadows, you get all these little rings on the ground. It seems to me it's almost more amazing to look at the ground when you're at an annular eclipse than it is to look up there. So, okay, we know one thing that makes eclipses long. The moon has to be relatively close to us. We also know that the moon has to be at a node. If I am now the Earth rather than the sun, and this is the orbit of the moon, it's tilted, you see. So it's as the, I'm going to think geocentrically for a few minutes, as the sun is going around there, every year the sun will be in the direction of this node. And so an eclipse will occur. And 6 months later, it will be over on the other node. So every year, there must be at least 2 eclipses of the sun. But often they're partial and not a total eclipse. But every year, someplace, maybe in Antarctica, there's going to be a partial eclipse, and 6 months later, another eclipse. But you will only get a total eclipse if both the sun and the moon get on this node just right at the same time. So you have that particular constraint. First of all, you have to get them lined up. But what if you line them up at the wrong place? Well, what about the moon coming close and so on? What's interesting about this is that the moon's nodes are going around this way very, very slowly. So it takes roughly 19 years for it to get around. If it were fixed like this, eclipses would always take place in the same month. Let us say in June and in December. But because it is moving around, the times of eclipses will be slowly changing in the calendar, coming earlier and earlier each year. But the distance of the moon is going the other direction. And so its close point goes around in about 9 years the other way. So it goes twice as fast as the nodes turn. And this causes the rhythm that we see in the way eclipses take place. What we call a saros is related to that. There are 2 other ways that you get a long eclipse. And that is that the Earth is not always the same distance from the moon. And, from the sun. And David has already told you that we're getting one of these situations next January when the sun will be the farthest away. And that means, have I got it right? It's going to be closest, because it's just exactly the opposite of how you think it ought to be. That's
for the northern hemisphere.
In the northern hemisphere, the moon is closest, the sun is closest in December. But in the southern hemisphere, it's closest, and it makes things warmer in the summer in the southern hemisphere, and it also makes the winter colder. So it works that way. Anyhow, if you get the sun at its farthest point, that is to say in July, then the sun looks the smallest, and that makes a longer eclipse possible, because the sun looks just a little bit smaller. Okay, but there's one other factor, and that is the Earth is spinning around. It's spinning around in the direction that the moon is traveling. So if you're close to the equator, the spin factor is much better in carrying you along with the shadow. So if you want to find out when the longest eclipse is, you don't have to start tediously calculating for every eclipse. You simply have to look for an eclipse that's total in June or July and near the equator. And if you do that, then you get a long eclipse. And let me show you the pattern here. Okay, the longest in 3 centuries took place on the 30th of June, 1954. It was 7 minutes and 8 seconds long, but you had to be in the right place for it, because throughout the entire path of the moon, it doesn't always work out that it's the same, the length. You get one spot that is the maximum. Now, if you want to get one that's longer than that, you have to wait until 2150 to get one that's a little bit longer. And if you want to get a really long one, 2 Saros cycles later, it goes up to 7 minutes and 29 seconds. Now, I've known eclipse chasers who don't just count how many eclipses they've been to, but they count how many seconds of totality they've seen. So there we were, down in Baja California. It was not quite as long as that one in 1955, but it's still one of those really pretty long ones. People came here to Baja California, and they went up into the mountains because they was closer to the central line, and they got a few seconds more. But what they didn't count on was the height of they weren't very high mountains, but as the moon begins to block the sun, it cools things down. And the cooling brought about clouds. And they just grew out of nowhere, and those guys who went to the hills had fewer seconds of totality than we got on the beach. I couldn't miss just showing you that picture. Now I've got to turn to Mars, because a few years ago you heard these reports again in the newspapers about this is the closest Mars has been in centuries, and so on. So that's another one of those calculations. How do you know when Mars is going to be the closest without sitting down and calculating where Mars is every single day for a few centuries? Well, this is a little graph that was made by Johannes Kepler back early in the 17th century. And he said, I was thinking I would call this a ball of yarn. But he said, this is how Mars appears from the Earth. It's one of these geocentric patterns like I showed you for Venus. But Kepler says that's all in one plane. So he said, I'm going to call it instead, and then the Latin expression was panis quadragesimalis. I knew that panis means bread, but quadragesimalis, 40 days, that's Lent. So I studied up the history of pretzels, and in fact, they were made as favors for German children during the Reformation, and they were passed out as a Lenten favor. So here we have a Lenten pretzel. And you can see how sometimes Mars gets much closer than other times when it does these close loops. So you can work it out because Mars's orbit is just a little bit eccentric to the Earth's orbit. There is a time when Mars can come closest, and it must happen in August. Now, suppose that Mars and the Earth are there at exactly the same time. Then we have a chance for Mars to be the closest in quite a few years. But let us let 1 year pass, and the Earth goes around and comes back to that same spot, but Mars is not there. It is going slower, and it takes a while. So you let the Earth go around again, and Mars bypasses it, and it won't come back and get there approximately for 14 years. In fact, if you work it out more carefully, it comes out to, maybe I should have said 15 years, it's something like that. In 32 years, you'll get a really close approach again. So all you have to do is check out the positions of Mars every 32 years. That's about 3 times a century, and you nail it down as to which the closest approach was without doing the calculations for the other 97 years. All right. I just wanted to show you that Kepler pretzel because Kepler's kind of fun with respect to transits. Kepler was interested in tracking the motion of the planets, and one day he was looking at the floor of his loft, and apparently there was a crack in the ceiling, so that the sun was projected onto the floor. And looking at that projection, he saw there was this little spot. Now, he had never heard of sunspots, but this must be one, like David mentioned, as being a whopper that's bigger than, several times bigger than the Earth, and you could get a pinhole projection. So he shows how the pinhole projection in the roof worked, and it put it down on the floor. He could see that he was getting a projection because when clouds came by, it also affected the image on the floor. He thought it was the planet Mercury going in front of the sun. He was so excited that he rushed out of his house, across the bridge, and up the castle hill to tell the Emperor Rudolph II that Mercury was going across in front of the sun. I suppose by the time he got up there, it was cloudy, and so the Emperor couldn't see it. By and by, Kepler realized that that was impossible, that Mercury couldn't have been in front of the sun that particular day, but he got interested in this kind of thing, and so he worked it out that, in fact, in 1531, there was to be a very close possibility of a Mercury transit and also a Venus transit in the same year. And so here is his little book, an admonition or a warning to astronomers to be alert for this very rare, miraculous thing in 1631 when Venus and also Mercury were going to cross the sun. So, unfortunately, Kepler died in that year in 1530, and so he didn't have a chance to look for it. In general, it was cloudy in Europe, but in Paris, an astronomer named Gassendi looked for it, the predictions weren't all that precise, had to be on guard watching for it for a couple of days around that time, and then did see the transit of Venus, the transit of Mercury. And that was the first time that somebody actually had a telescope and was able to observe this. This became a very important thing for understanding that Kepler's tables were the best in the business. And it helped credential what Kepler was doing. Now, the transit of Venus. Well, let's just think about that date. Cambridge was founded, I believe. But I don't think there were any telescopes here. So the transit of Venus took place. It could have been seen in America, but apparently nobody got it. It was invisible in Europe, and so that one was missed. But Kepler made the calculation, and he somehow thought that it was probably going to miss 8 years later. But in fact, his tables did show it was awfully close. And with honing them a little bit, it became plain to a precocious young Englishman named Jeremiah Horrocks that maybe the planet would indeed come close as Kepler's table showed. So he watched very, very faithfully, starting, I am sure, a couple days early, for this phenomenon. And with great joy, he then saw Venus on the face of the sun. There you see his telescope. How the light is coming in horizontally to the telescope, I have no idea. It is a little bit imaginary, I think, altogether. Unfortunately, though Horrocks was very precocious and did a lot of interesting work, he died in his early 20s. And so his work did not get published until it was discovered by the astronomer Hevelius, and it was then published, and it shows how Hevelius thought Venus would have appeared on the face of the sun. Following this time, the astronomer Edmund Halley realized that a transit of Venus could be an important way to get the distance to the sun. I'll explain that a little bit better in a moment, but let me say that unfortunately he was not in a position of waiting it out because these transits of Venus were so far apart. The next one to come was in 1761. And by that time, astronomers worldwide realized that this would be an important phenomenon to observe. And so they set about trying to get a worldwide group of observations. And you have to understand that you had to observe it from distant parts of the Earth in order to get the triangulation required for the getting the distance to the sun. So in 1761, leading up to it, there was a great effort made to try to send expeditions to distant points armed with telescopes and clocks so that they could make these observations. And there's a wonderful letter written by one of the members of the Royal Society to get funding for this event, to send the expeditions out. And as I read this to you, just think about the competition between the U.S. and the Russians about trying to get to the moon first or this kind of thing. My Lord Duke, I did myself the honor this morning of calling at your Grace's door with an intent to lay before you the enclosed copy of a memorandum from the Royal Society, which I believe will be presented to the Lords Commissioners of the Treasury at the next meeting. The memorial itself plainly shows that the motives on which it is founded are the improvement of astronomy and the honor of this nation, which seems to be more particularly concerned in exact observation of this rare phenomenon that was never observed but by one Englishman, and pointed out and illustrated by Dr. Halley, another Englishman. And it might afford too just a ground to foreigners for reproaching this nation in general, not inferior to any other in every branch of learning and more especially in astronomy, if, while the French king is sending observers not only to Pondicherry and the Cape of Good Hope, but also to the northern parts of Siberia. And the court of Russia are doing the same to the most eastern confines of Greater Tartary, not to mention the several observers who are going to various places on the same errand from different parts of Europe. England should neglect to send observers to such places, subject to the crown of Great Britain. This is by foreign countries in general expected from us because of the use that may be derived from this phenomenon and will be proportionate to the numbers of distant places where observations shall be made of it, and so on. Well, so that's the background for the effort which was being made in 1761, and I've just posted 3 places among the many where observations were made because these were of particular interest. For example, here in Cambridge, it was right on the line where it would be invisible. And so John Winthrop, who was one of the leading astronomers of the colonies, made an expedition up here to Newfoundland specifically in order to see it. In France, one of their astronomers, a Jesuit named Chap, went out here to this point in Siberia. It's not the far distant Siberia, but it's right in here, Tobolsk. And then another Frenchman, Lei Zhang T, was headed to Pondicherry, which is here in southern India. His was a very sad sort of situation because Pondicherry had been in French hands, but while he was on the high seas getting there, it was captured by the British. And even though he had letters of safe passage, the captain of the ship was afraid to go there. And it ended up that poor Lei Zhang T was on the high seas. He saw the transit, but his observations were useless because you had to know precisely where you were making the observations from. And in addition, you had to be able to precisely time them. And a pendulum clock on a rocking ship does not work very well. So there he was. So he decided that it was okay. He would explore this part of the world and stay there for 8 years and wait for the next one in 1869. He had been over, among other things, exploring the Philippines when the word came from the French Academy of Sciences that he should go back to India to do the observation. It was, in fact, wonderfully clear weather on the days leading up to it, and then on the day of the transit, the clouds rolled in, and to rub salt into the wounds, back in the Philippines, it was perfectly clear. So it's a very interesting story because by the time he got back to France, he was assumed to be dead and his estate was being divided up. He had to go to court to get his place back again. Well, so now they learned a lot on that first great international set of expeditions. There were problems, and I'll come back to some of those later, but everybody was much better prepared for it, and they had a longer lead time. And I'd like to just mention 3 of the expeditions that went heroically to distant parts of the Earth in order to get a long enough baseline for this observation. So this is Maximilian Hell. He was a Jesuit from Vienna. He got a special invitation from the King of Norway to see it in Norwegian territory. He went up well in advance through very wintry weather. It was an ordeal, and particularly here on the ocean of the Norwegian Sea, to get up to this, practically to the tip of Norway, to Vardø, where he was for a substantial length of time getting ready for this event. You can see out the window the wooden buildings, which were part of the setup, and here he is with his Laplander costume to keep warm in this bitter part of the earth. He was happily successful in having good weather. And so he got some very important observations, although he made the French and some of the other people back in Europe kind of peeved because he felt very strongly that he had to present his observations first to the King of Norway. And so he didn't just rush into sending them out to everybody who was trying to make the calculations. So it was a little bit fraught there. Now let me explain what the idea of this is. You want to observe the position of Venus as seen crossing the sun from two different stations on Earth. And you want to get them separated as far from each other as possible so that you have the largest baseline here. You know the ratio of the distance to Venus and the distance to the sun. So this fulcrum of these parallel triangles is well known, and all you're trying to do is to establish one of these distances so that then you know the entire distance to the sun. Now, the sun doesn't have any markers on it to know exactly where that line is going. So the idea was you have a clock and you record the moment Venus comes onto the edge of the sun and exactly how long it takes to get across. And of course, excuse me, the shorter the time, the shorter the line across the sun is, and so you can place it exactly where it fits. The difference in the trajectories between two different points on Earth, they're very, very close together. This is a huge exaggeration. The scale is quite wrong here. So you don't understand from this diagram how extraordinarily sensitive it is for getting the length of time it takes to go across. And then you must also know very precisely where you are on the Earth so that the distance between the stations can be calculated. Okay, let's go on to another one of these expeditions, and that is by Chap d'Auteroche. He was also a Jesuit, a French Jesuit, who had observed successfully the beginning and end of the transit in 1861 from Siberia, and he was going to be very courageous and go off to Baja California in order to get a strong enough baseline. And as it worked out, he was the only person who was able to record the ingress and egress, that is the entrance onto the sun and the exit for both of the transits. So let's see where he worked. He came here to Mexico, through Mexico City, over to the port, and then a great slowdown because the winds were not favorable, even though the distance was not that long. So that's partly why it meant sailing up north and coming back down in to get to San Jose del Cabo, right there at the end of Baja California. Well, while Maximilian Hell was freezing and had all these snowstorms and everything to cope with, it was just the opposite down here. It was a mosquito-ridden, swampy place, hot, sweaty. It was a terrible kind of situation, and people started dropping like flies from typhus. But he hung in there. He made the observations. He got them down into his notebook quite accurately. He stayed to make further observations to get the geographical position established, and then came down with typhus himself, and he died in 2 weeks after putting the last observation in his book. Well, that's one of the very sad stories about this great adventure. And now another fabulous point to go to, and that was Tahiti with Captain Cook. This was only the second ship to go into Tahiti after it had been discovered. So here is Venus Point, where he was, and here comes. He fenced off this particular area so that he could make the observations. It was it was very interesting. It was part of a round-the-world expedition. And so he carried out a very important medical experiment. They loaded up a huge amount of sauerkraut. Now, it turns out that in those days, if you were manning a round-the-world expedition, you would take on twice as many sailors as you really needed, because you figured that half of them would die of scurvy on the trip. Now, how to get the sailors to eat the sauerkraut? Captain Cook allowed it only for the officers. When the seamen saw the officers eating that and were being deprived of it, they demanded that they should have this. And so as a result, they even asked for seconds. And they did not lose a single sailor to scurvy on that important trip. Here we are at the point where the fort had been placed for making the observations, there at Venus Point. On the way back, they stopped in Australia. And so I always point out that even these exact esoteric sciences have unexpected practical results. This is technological fallout from this expedition to observe Venus, namely the discovery of the eastern half of Australia. So there's the ship is being beached for repairs because getting in across the Great Barrier Reef was a little risky. Ran some problems in the keel, but they got that sorted out. Well, I have to say that was pretty interesting for the getting the exact results. But I suspect somehow I forgot to put one of the slides in that I had particularly made, unless it's someplace out of order. That is to say, when Venus was coming onto the edge of the sun, something strange happened. Instead of just making a very clean break as it got tangent to the outer edge of the sun, there was as if a little black thread held, and then suddenly it would pop, and you would realize that, oh, it's already on. We've missed it by a few seconds. And this is called the black drop effect, and it bothered all of the expeditions, so that you could have two people observing side by side with different telescopes, and the estimate of when that exact happened could be as much as 1 minute difference between the two observers. And this meant that the observations were not as precise as expected. So that as a result of this, there was a lot of ambiguity about getting the distance to the sun. If you took the results just of those 3 expeditions I've pointed out to you, and used the best results from each of those, you would get a result within 1% of the today accepted distance to the sun. But of course, nobody knew for sure that those were the 3 observations that you should use. And there was a lot of nationalism involved as to whose observations you wanted to weight the heaviest. So there was a lot of ambiguity. So now we come into the 19th century, and I'm showing you a picture of Harvard Observatory, but not as it appeared in 1884, because here we are in the building that now stands in front of Building C, but Building C wasn't built yet. It wasn't built until 1893. But there were a lot of telescopes out here, and let's see what Professor Pickering, who was running the observatory, had to say about all this. Cambridge was not selected by the United States Commission as a station for observing the transit of Venus. This was in some respects unfortunate, as a complete series of observations were made here in 1878 of the transit of Mercury. This was at the request of the Naval Observatory, with the expectation that we should thus be prepared to observe the transit of Venus at the present time. On the other hand, it is extremely doubtful whether the results obtained during the transits will materially add to our knowledge of the distance of the sun, and the chance of a cloudy day is twice as great as that of a clear one. I regard the expenditure of money on large pieces of routine work where a result of value is certain to be secured as more advisable than any large expenditure for observing occasional phenomena where clouds may prevent the attainment of any result. So they didn't make a big deal of it. There's a little bit of sour grapes, I think, there. But in any event, I misspoke the date a little bit ago. It was 1882. For reasons stated in the last report, no elaborate preparations were made at this observatory for observing the transit of Venus on the 6th of last December. But as the weather was favorable during most of the day, a considerable number of observations was obtained. 6 telescopes were employed in observing the contacts, etc. So observations were made here. But the results, again, were not as accurate as hoped, because this so-called black drop effect was affecting stations all over the world. And eventually, other good methods came for getting the distance to the sun, including today radar and results from the space expeditions to the other planets. By being in communication with them, you get a very good scale of the solar system. Anyway, nowadays these things are great tourist attractions. I looked at the weather map of Europe, saw that the farther south you went, the better chances you had. And so last time I was in Palermo to see the transit. Now, watching a transit, and here you won't be able to see but a small section of it, I have to say is very much like watching grass grow. It's fun to see it, but then what? It's on the surface. There the planet is showing on that spot. And now here's a very fuzzy image, but this was in the Palermo Cathedral, where they had one of these sort of sundials where a small aperture allows a pinhole image of the sun to fall on the floor of the cathedral. And there, very fuzzily, is Venus just about to go off the edge of the sun. Slightly blurry there, but very interesting to see it under those circumstances. On June the 6th this year, I shall be on Mount Wilson Observatory, where there will be an alignment of telescopes, and I will be giving this same lecture to people there on the day of the transit. I'll put in the black drop effect, which I've forgotten about here. So here you can see that in this part of the world, you don't get the whole transit, but you get part of it. And so the closer you are to this line, the more of it you will be able to see before the sun sets. If you want to get to the whole transit, you can think about going out here someplace in the Pacific. How about Papua New Guinea? Anyway, there are these possibilities. But I have still, I think, David, do I have 6 more minutes before I'm thrown off?
6 minutes.
6 minutes, just exactly what I need. Because while the transits of Venus are today more of a tourist attraction than a scientific goal, transits are playing a huge role in the science which is being done here at the CFA. It's one of the world's leading places for this work, although it's being done in other places as well. And here is where a lot of the work is pouring in from the so-called Kepler Mission. It's appropriately named because of Kepler's interest in things like this. In this field of view, alongside the Northern Cross, here just on the edge of the Milky Way, there is a constant watch being made of the brightnesses of about 100,000 stars, I think. I've got the right number. Okay. So when you're above the atmosphere, you don't have the twinkling of the atmosphere interfering. It's possible with the electronic detectors to observe very, very closely if there's any change in brightness of these stars. And how could there be a change in brightness? Well, there are many ways that stars can vary. But one possibility is if they've got a planetary system, a planet might go in front and therefore cause a dimming of the light in a very characteristic way that would be representative of a planet crossing. Now, if you get such a thing, you obviously want to be able to confirm it. If it's like the Earth, you have to wait a year for it to happen. If it's like Mars, you have to wait nearly 2 years. So what you're going to get is observationally planets that are relatively close to their primary stars. And this also means that they're going to be hot because they're so close to the stars. So the goal of this project is, in fact, to find Earth-like planets from some of those stars. But you have observational selection that is going against you in this. But still, there's a lot of hope in getting these things. Here is the way the list stood about a year and a half ago, where there were 827 with a single planet. But look, down in the list, you get up to systems of 4, 5, and 6 planets. The update last February was that they had got the number up to 2,300 candidate stars. As of today, the number has surpassed 3,000, but the release of data won't be made until October, so that's a secret. Here is one of those systems of 6 planets that made it to the front cover of Nature magazine. It's quite amazing that these multiple systems are being discovered because it gives a lot of information as how the planets can gravitationally interact with each other. It also gives the idea that a fair number of these systems are coplanar. You have to have the plane, of course, tilting in such a way that it's more or less edge-on to the Earth. Otherwise, if the planets were going up and down and around, we wouldn't see any transits. So only a fraction of the stars with planets are going to be detected by this method. But still, the yield is really quite surprising to get so many. And then here is a fabulous one, which they got about a year ago, a little bit more, where it's a system that has 2 suns in the sky and 1 planet found so far. You have a small reddish cool star going around a more solar type of star, the so-called Kepler 16 system. So that's where the red-hot subject is now. So transits are quaint, they're wonderful historically, they're fun to go and watch a phenomenon that is so very rare. But where the action is these transits that are being sought by this particular space mission. This slide comes from Harlow Shapley, who was director of this observatory, was director when this building was built. He was responsible for making sure that they had all of the planet names going around, because the very recently discovered planet, Pluto, was in need of a symbol, and they made a symbol just in time so that the balcony railings could have the PL there in that list. This is a place where Shapley reigned for a long time.
Owen, thank you.